NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How is everyone tonight? Good, excellent. Thank you, you're far too kind. Well, thank you everyone, both here in the house and on camera and on the internet and all that, for joining us tonight. So tonight we celebrate the 60th anniversary of Explorer 1, the first US satellite which also made the first science discovery in space and paved the way for 6 decades of Earth science discoveries. As you can see, our setup tonight is a little bit different. We'll be using a panel format hosted by JPL's Blaine Baggett. But with our usual lecture format, you'll be able to ask questions after the show. Blaine is a JPL fellow and the laboratory's documentarian. His productions, many involving space themes, have been recognized by virtually every major awards competition, including the DuPont Columbia Award for Journalism, the Peabody Award, and local, national, and international Emmys. Ladies and gentlemen, please help me welcome tonight's host, Mr. Blaine Baggett.
Good evening, and let me also extend my welcome to you to NASA's Jet Propulsion Laboratory here in La Cañada, California. We are going to celebrate Explorer 1, the very first US satellite, and the satellite that gave the entire world the very first space science discovery. And it was discovery, not just any science discovery, but one that helps to explain why you and I can walk on the surface of this planet. So I think you'll be very interested in knowing about it. And then in the second half of our show, we're going to speed ahead 60 years and spend some time learning about what do we know about the vital signs of our planet now and what NASA is doing to understand that. So to begin, let me introduce our historian, Dr. Erik Conway. Will you come on board here? Erik? Good evening, Erik.
Good evening.
Just by a small introduction, Erik is our official historian here at the laboratory. You know, he's a published author. He's written things about Mars, about aviation, and about our own planet. So just as a context about how JPL got started for everyone, and then we'll leap ahead, is that JPL started as a small group of handful of students, some of them Caltech, who wanted to build rockets in the 1930s, and that got serious during the drumbeats of World War II coming on. There was funding from the Army, and it was actually an Army exercise to build rockets to begin, wasn't it?
Yep. The lab basically started as a student research project and kind of grew like Topsy after 39, yeah.
And we're going to leap ahead to this iconic image we have up here for us, which is the celebration of the success of Explorer 1. And let's start off, Erik, by who's that fellow on the far right that we see here?
So the gentleman on the far right is Wernher von Braun. He got his start designing and building rockets for Nazi Germany. Started really in the 30s, began to be successful really in the mid-40s, and was able to get his V1 and V2 rockets to a state where he could bombard London during the war. And after the war, he and a large group of his engineers and scientists with him decided to surrender to US forces in Germany, basically because they figured they would be better treated for us and that we were more likely to be able to afford their ambitions to build space rockets.
And that's indeed what happened. They went to the United States to, I guess, first New Mexico, and they were launching these V2s as experiments in the United States.
That's right. That's right. So the U.S. didn't just abscond with von Braun and his engineers. We also brought back about 100 of the V2s that had been built in various stages of repair, and they were shipped to White Sands Proving Ground in New Mexico, where the Army had them reassembled and began test launching them, along with instrumentation prepared with the help of a group of U.S. scientists known as the Rocket Research Panel.
And then they move on to Alabama.
Yeah, they eventually land in Huntsville, Alabama, but White Sands is where they first came into collaboration with JPL, which was also developing its ballistic missiles for the Army via test launches at White Sands.
And how about, let's go back to the image here, and what about the fellow on the far left?
So the gentleman on the far left is a New Zealander who came to Caltech to get his PhD in electrical engineering, did cosmic ray research, and then began working part-time initially at JPL on telemetry for the missile program here at the lab. Became the Corporal Missile Program Director. Corporal was a JPL liquid-fueled rocket being developed as we would now call it a short-range ballistic missile with a nuclear warhead for deployment in Europe. He became the Corporal Program Director, and then in 1954, he became the JPL Director.
So you've got these two groups, one in Alabama, one here at JPL. They're both building rockets, and they somehow merged their ambitions.
Merged not just in terms of their ambitions, though, but in terms of the actual hardware. One of the things that was known to be possible theoretically but hadn't been done as of the late 1940s is staging. We do it all the time now. But here you're looking at the actual first product of the union of JPL and von Braun's folks in what was called a bumper whack. Literally, the lower half of this rocket is a V2, and the upper half of it is a JPL-built whack Corporal. There were 8 of these flown, the first 6 at White Sands, and the last 2 at Cape Canaveral. This one is known as bumper whack number 8, which was launched from the Cape in July 1950.
And this was the very first ever launch of a rocket from the Cape.
Yep.
Amazing, yes. And so they get this notion that they want to launch a satellite into space, don't they?
They kept working together after this bumper whack program. The Army had them working because of pressure on all the U.S. Armed Services to develop ICBMs. They had a research project to figure out whether you could bring warheads back from space intact, which was known as the Reentry Test Vehicle Program, was classified for a long time. They built, I believe it was 9 sets of hardware that were a Redstone rocket and a set of upper stages, solid-fueled upper stages developed by JPL to hurl a warhead a few thousand miles downrange and fast enough to prove that you could bring this warhead back from space. And they also believed that that set of equipment could be used to orbit a satellite. They proposed this as Project Orbiter.
But Eisenhower, who's president, we're in the midst of the Cold War here, has other agendas, and let's roll a video, a clip from a documentary that's been done on Explorer 1.
Nikita Khrushchev had rejected Eisenhower's open skies proposal to use airplanes for mutual reconnaissance. How hostile, Eisenhower worried, would the Soviet Union be to a satellite flying overhead?
The great question hanging over the inauguration of the space age was, is it legal to orbit satellites over the territory of other countries? Is outer space subject to the same airspace laws that airplanes have to obey? It's not legal to fly U-2 airplanes over the Soviet Union if the Soviet Union doesn't permit it. Their airspace is an extension of their national sovereignty, extending upward. Usque ad coelum, in the Latin phrase, even unto the heavens.
In 1955, a potential solution to the problem appeared. Physicist James Van Allen was helping spearhead an effort to launch a satellite to study the Earth as part of a worldwide science effort called the International Geophysical Year, or IGY. Eisenhower immediately seized on the opportunity.
So that fellow is the fellow we see here in the center of this picture. So tell us about James Van Allen and the role he's playing in this story.
So Van Allen is another early cosmic ray researcher, and along with JPL director William Pickering, was a member of the Rocket and Research Panel that was flying instruments on these V2s. He was also a developer of small rockets to do cosmic ray research, even a thing that called a raccoon, of all things. Literally a balloon with a rocket under it. You sent the balloon up. When they got high enough, launched the rocket. So Van Allen was already deeply involved in this kind of rocket research, and he knew Pickering. Van Allen's cosmic ray instrument was selected for the International Geophysical Year orbiting satellite after that was approved by President Eisenhower, and I believe it's 55. And so he was very involved in that whole research area and in getting it sold. One of the problems the International Geophysical Year scientists had was that they wanted to do global measurements, even in Antarctica. But from the ground, the best you can do is get a bunch of pinpricks on the surface of the world. And with a satellite, you could do much better. So that was the idea of the IGY satellite program that Van Allen helped sell.
So he's advocating that.
He was certainly an advocate of it.
And Pickering is gung-ho, as is Von Braun. But the Russians are interested in this too.
That's right. That's right. So the International Geophysical Year actually had a lot of Soviet connections. They had major research fleets. They wanted to appear scientifically interested and progressive. So they intended to contribute a lot to the IGY, and they decided they were going to launch their own satellite.
And lo and behold, they do, to the shock of the entire world.
The shock of the entire world, except the people who knew a lot about the IGY, because they actually announced in advance that they were going to do it. It's just people didn't pay that. The rest of us just didn't pay attention.
Right. And so.
And I think it was very surprising to most Americans, even the ones in the know, that it actually worked.
It was a shock, really, to the system. People had to take math. I had to take math as a result of this.
Yeah, that's true. There was the National Defense Education Act after that.
So at this point, we did have our own satellite our own program, and it was called Vanguard, I think.
Yep. So the Vanguard program, remember I said earlier, I think, that Von Braun and JPL's folks had proposed something called Project Orbiter to use that vehicle stack, we like to call it in the space business, but that rocket they developed for the reentry test vehicle program to orbit a satellite. And they proposed that as the International Geophysical Year's launch vehicle, and they lost. You saw in that the tape, it's the wrong word for it, but you saw in the tape, Eisenhower had this concern about overflight. And because he had that concern about overflight, he wanted the US IGY satellite to have as little connection to military programs as possible. And so the Naval Research Lab proposed developing a new rocket that wasn't a result of the ICBM program for the IGY. That was called Vanguard, and that was the vehicle that got the blessing of the White House.
And then what happened on the launch pad?
Well, there's a reason that little satellite you saw is hanging in a museum now instead of burned up in space. Their launch vehicle exploded.
In front of the whole world on television?
Yeah, because the U.S. didn't keep it all secret. We had a very public embarrassment.
It was called Flopnik.
Flopnik and Kaputnik, yeah.
So at this point, Eisenhower has really no choice but to turn to the efforts of JPL and what was then, I guess, Redstone with Von Braun.
That's right. So after the Sputnik launch in October, President Eisenhower had authorized a backup to be prepared using the Army JPL Von Braun group's reentry test vehicle setup, like Project Orbiter, except with Van Allen's cosmic ray instrument and a couple of micrometeoroid detectors. And that launch attempt is what winds up pulling JPL out of the classified world and back into space science.
So let's go back to that actual time and see the launch and see what happened.
Time, late evening, Friday, January 31st, 1958, in a blockhouse at Canaveral. The countdown to Explorer 1.
Roger. Okay, we'll start now.
Any fuel loading?
I don't have it yet. Range safe. Range safe. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Fire command. Fire command.
So we got a report from the Cape that the launch looks pretty good, and it should fly over California at such and such a time. And so the decision was made that we would make no public announcements about the rocket until it had actually been picked up in California. And so we sat there for an hour and a half. The time came and went, and there was a period of 8 minutes there, which was the longest 8 minutes I've ever spent in my life.
But finally, JPL received the signal that the satellite was in orbit. The United States had a success. Eisenhower, on a golfing trip at the time, was awakened from his sleep and told the news. "Let's not make too big of a hullabaloo over this," he cautioned, and went back to sleep. No one took the president's advice.
We were told that there was going to be a press conference over at the National Academy of Sciences on the other side of the river. So off we went, and I remember sitting in that car with the three of us in the back seat. It was sort of a cold, rainy January night in Washington, and I remember a conversation going along, I wonder whether anybody's going to be out here because it's now about 2 o'clock in the morning, you see.
In Washington, at the National Academy of Science, a packed auditorium of reporters, radio...
When Brown, and Alen, and Pickering are there to lift the satellite aloft.
The success of Explorer and what we learned from it really does kind of recreate in the most fundamental way the nature of the Jet Propulsion Lab, and moving it from a rocket development center to one in which space science becomes what it really does. It really put JPL on the map scientifically.
And there you have it, that moment, the iconic moment. And what's really important about it, I guess, is the space science as much. And talk to us about what that instrument was and what it did, please.
So Van Alen's instrument fundamentally is a Geiger counter in a cosmic ray instrument, and it's kind of the center tube of that image you're seeing. Well, I'm pointing to one down there because it's on the floor, but up there. And it's surrounded by batteries because there are no solar panels on the satellite yet. And it had an odd behavior while it was orbiting the Earth, and that was it would have a normal sort of expected lowish count, and then it would start to climb, and then it would suddenly go to 0. And it did this in every orbit. And it's a couple of months before Van Alen's crew start to understand what's going on. They thought there's something wrong with the instrument. And they tried various things. But what was really happening was that it was becoming saturated when it got to certain parts of its orbit. And they tried in the lab to figure out what you had to do to cause this to happen. And they found if they zapped it with an X-ray machine, they would get the same result. And what that showed was that there's a point in its orbit where it's going through an extremely high area of radiation, and they figured that it's radiation trapped by the Earth's magnetic field.
So we have basically radiation belts.
We have a radiation belt and radiation shielding from the magnetic field that a handful of scientists had thought might be true, but disproved it.
And because of that radiation belt, we're protected.
We're protected by it, yeah. Yeah.
And from the cosmic rays, and we're able to walk around there here on the
Might
surface.
be key to life on Earth.
That's right.
Might be.
Yeah. Well, that's a great story. And then there's another thing that happens as a result of this, is that there's the formation of our space agency.
Yeah, so President Eisenhower having, it's the Army, his old service, of course, the Army who had had the first space science result. But President Eisenhower didn't want science kind of under the military's thumb, even if the military had been a good patron. And so he took some thought on the subject of how to go about making a civilian space agency that would be a scientific agency as well. And concluded that the way to go about it was to take an already existing organization known as the National Advisory Committee on Aeronautics, or the NACA. It's actually been founded right at the end of World War I, and convert that into the new space agency. And that's 4 other centers, but not JPL and not the Huntsville folks initially. So at one point, it looked like Caltech and JPL would just be shut out of the space age.
But JPL, particularly because we're a part of Caltech to this day, wanted to get out of the weapons business and wanted to get into the science business.
Absolutely. So Caltech had never been very happy with the decision that the Army made to convert JPL into making weapons for the Cold War. And particularly not when they started making operational weapon systems, because it didn't contribute to the teaching mission of Caltech. It's a school, fundamentally. That's what it's supposed to be. And so there were discussions about how do we get JPL to do something else, and this was the opportunity. So NASA goes into operation in October of '58, and Mr. Pickering, or Dr. Pickering, I'm sorry, will be crucified for that. Dr. Pickering goes to Washington to try to sell NASA and the White House on the idea of moving JPL out of the Army and into NASA. And they're successful. So JPL makes the transition of the beginning of the following year. But it took the von Braun's crew another couple of years to even decide they wanted to be out of the Army and move over to NASA.
Was to turn on a twist of a phrase is the rest is the future.
The rest is the future, and we do things that are completely different now.
Erik, thank you so much for
Thanks
this
for having me.
whirlwind tour. Thank you. Thank you. And now we're going to turn our attention to some incredible software that I couldn't be more proud of that you can download on your computer, in some cases on an application, that you can see some of the things that we're doing today in space exploration. And to tell us about that is Mr. Jason Craig, a visualization specialist here at the laboratory. Welcome, Jason.
Thank you, Blaine. So if you've been watching this monitor, you've seen Explorer 1, but what you may not know is this is not a pre-rendered animation. This is a live 3D simulation in real time. So this is 1 second per second, and I can control what's going on. So this is actually the entire solar system from 1950 to 2050, and you're in control of time and space. So if I leave Explorer 1, there's not much going on out there, out in the solar system. But I can turn on the labels, the orbit lines, constellations if you like. And if I hit the Now button, we can see where everything is. Let's turn off those constellations. So I'm going to use the controls to show you some cool stuff. But first and foremost, I want you to know that this is something that you can have at home. So in the back of the room, there are cards that will tell you the website to go to, and you can download this for your PC or Mac, laptop or desktop. And it's called Eyes on the Solar System. And it's at eyes.nasa.gov, eyes like your eyes. And you actually get 3 programs when you do a quick install. So I'm showing right now, I was showing Eyes on the Solar System, which is the simulation of over 120 NASA missions for 100 years. And it's accurate. It's accurate as it can possibly be. Everything's to scale 1 to 1 to 1. You also get Eyes on the Earth, which I'm going to show after this to show some Earth data. And you can visit each and every exoplanet we've ever found, which is over 3,000. I wouldn't advise that unless you've got a lot of free time. But those are just for your laptop or your desktop, but we also have apps for your phone. So if you have your phone, you can actually get these right away. Earth Now, which will be similar to what I'm about to show, but it's for your phone. And also one called Spacecraft 3D, and I have cards in the back for that as well. And that's kind of fun. It's like Pokemon Go, but for NASA spacecraft. So check that out when you get a chance. So quick download, and you get 3 programs. Now let me show you some cool stuff. All right, so back to the solar system. Let me turn off the constellations and go back here. And this is a live view of the solar system. We hit now. It's January 25th, 7:29 p.m. at 1 second per second. So let me show you, turn on the orbit line so you can see the solar system. So there it is. This is the solar system. I'm in control. We can pull out all the way to the Voyagers. The Voyagers, this one has left the solar system. But let me go to Mars. Let's just drop in on Mars and take a live look. Any label you see, you double click and you go on in. And this is Mars right now. And those are our missions at Mars right now. There's actually quite a few. And let me fast forward so you can see. So that's 7 minutes per second rate. So we've got a bunch of orbiters. You can see the moon there, Phobos, and we have 2 rovers on Mars right now. Let me show you the trails of each of these orbiters. So let's go double click on one and take a look and see how it's doing. I can catch MRO here. Boy, that's fast. Let's go back to real rate. Sometimes they run away from you. Let's go to Odyssey. Odyssey is a very long-lasting orbiter. So there's Odyssey. This is actually where it is this very second. And if you want to go ahead in time, we just fast forward. If you go really fast, you can make yourself ill. But we're not going to do that. And let me go back out and show you something you may not be aware of, is the beautiful shadows on Saturn. So we have added this detail. Let me bring up real lighting. These beautiful ring shadows on Saturn. They're amazing. And this is what they look like right now. But if we go forward in time, you can see what happens with its seasons. And now it's changed to the northern hemisphere. So now we're in 2028. So just like that, we're there. But let me fast forward some more. We get back up to the absolute solstice, and then it'll go back down again. Pretty cool stuff. But I'm going to leave solar system because the rest of this will be Earth. And I'm going to switch to Eyes on the Earth. So when you install, you get all of these programs. It'll put a little icon on your desktop, and I'm going to load Eyes on the Earth and show you our Earth fleet right now. So this is a live look. If I hit real time, this is a live look at our Earth fleet. And so Eyes on the Solar System, this is for you, good taxpayers. You've already paid for it. You may as well download it. So please check it out when you get a chance. I'll turn it back over to Blaine now.
Thank you, Jason.
You're welcome.
That's the fastest trip I've taken through the solar system ever, I think. Well, joining me now are 2 incredible scientists here at the laboratory, Dr. Carmen Boening and Dr. Erika Podest. Dr. Boening is a scientist on the GRACE mission. She's conducting research on ocean climate interactions that include global water cycle and sea level rise. And Dr. Podest is working on the Soil Moisture Active Passive Mission, a mission better known and easier said as SMAP. Her research areas include global carbon and water cycle changes and climate change. So welcome to you too.
Thank you.
Now, we've got a lot of ground to cover, and atmosphere and oceans to cover. And so let's get right to it. Jason's going to continue to visualize what we're talking about as we go through this. But he's put up on the screen this armada of science instruments that are circling the globe now. It's quite an impressive group of missions here.
Yeah, absolutely. So what you're seeing here is NASA's Earth-observing missions in space, which consist of 20. And these missions observe the different components of our global environment as related to the oceans, the atmosphere, and the continents. And together, they provide a picture of our Earth as a system. So we can study almost everything, from the air we breathe to the rain and the snow that provide water for agriculture or for communities, to natural disasters like floods and droughts. And the study from space has really revolutionized our understanding of our planet, and it's constantly providing new information that helps us understand how the planet functions and how it's changing. And all of this is thanks to the incredible technological achievement that's been developed through decades of experience, going back to Explorer 1.
And I know a favorite image that you have is of the Earth as a puzzle. As a scientist, that makes sense to me because there's such mysteries I know you're always wanting to solve. But it's a complex system and a complex puzzle to solve, isn't it?
Yes, absolutely. So the pieces of the puzzle are everything. Urban environments, biodiversity, oceans, atmosphere, everything that comprises our planet. And putting this puzzle together is complicated because Earth is a complex system. There's a lot of interactions at different scales, from the local to the regional to the global scales. And it's not only that, but it's understanding what happens when a system is altered, how that impacts other systems, and then trying to foresee how things will evolve in the future. So even though we don't know everything, we have enough pieces of the puzzle to know the general direction where things are heading.
So, Carmen, we're going to be talking a lot about climate, but I just want to make sure we are all clear about the difference between climate and weather, because we've had a lot of cold weather in this country recently, and I can imagine a lot of folks shivering, saying, what do you mean about the fact that the climate is warming? What is the difference, really?
Yeah.
Just be clear between
exactly,
the two.
yeah. So there is a big difference between climate and weather. And weather is really what's happening right now in one place to the other. And as you said, it might be very cold somewhere in the world. And then at the same time, there is a lot of heat and droughts in another place. So looking at these things over time, that is what climate is. It's really not the hourly to daily, weekly weather, but the long-term change. What happens from year to year, from decade to decade, maybe even over centuries. And that's like so great now that we have this fleet of satellites that can actually look at the whole globe and look at these different places, how they develop over time. And yes, just have this big picture view of everything.
And you know, and you mentioned decades. If we just think about this new century, just recently NASA announced that something like 17 of the last, I think, 18 years have been the warmest in modern records. And this all goes back to another basic ideal, fundamental ideal of the greenhouse effect, isn't it?
Absolutely. So the Earth is surrounded by a layer of gases called the atmosphere. And some of these gases are greenhouse gases, which trap heat. The greenhouse effect, what you're seeing here, is when the sun heats up the surface of our planet, the surface then radiates that heat back to the atmosphere. Part of that heat is trapped by the greenhouse gases in the atmosphere. And what you're seeing on the right is what's called the normal, it's the normal greenhouse effect. And what you're seeing on the, on the left, what you're seeing on the right is the perturbed greenhouse effect. So what's happening is, think of it as a blanket. And as we are increasing the concentration of greenhouse gases in the atmosphere, that blanket is getting thicker. And therefore, the ability of Earth to trap heat is increasing. And that's the perturbed greenhouse effect that you're seeing on the right. The greenhouse effect is natural here on Earth. If it were not for the greenhouse effect, we would not be able to live here. So it's very, very important. And what you're seeing in this graph are the gases that make up the greenhouse effect, which are water vapor, carbon dioxide, methane, nitrous oxide, chlorofluorocarbons. However, the most important man-made greenhouse gas is carbon dioxide, or CO2. And CO2 can be released to the atmosphere either through natural processes like volcanic eruptions or through human activities such as the production of cement, deforestation, forest degradation, and the burning of fossil fuels. And that's one thing that JPL and NASA can do from space, is measure the concentration of carbon dioxide in the atmosphere. And what you're seeing here, this video animation, is the monthly concentration of CO2 starting from 2002 and going through 2016 as measured with a sensor called AIRS, and it's on board a NASA satellite called Aqua. The colors, the aqua colors, are lower concentrations of CO2, and the yellow and the red colors represent higher concentrations of CO2. CO2, by the way, is measured in parts per million. And you can see here throughout the progression of this video that there's been a change in the colors from blues to yellows and reds. So the next graph shows this quantitatively throughout the time period of the video. And we can see that it's just a continuous increase in CO2 concentrations. Where are we now? In December of 2017, the average CO2 concentration was about 406 parts per million. But what does that mean? So let's put things into perspective. The next graph shows reconstructions of atmospheric CO2 concentration through ice cores. And we go 500,000 years back. And we can see that in this time frame, CO2 concentrations didn't go above 300 parts per million. Okay? So that puts things into perspective. We are living in unprecedented times.
And the interesting thing to me, looking at this graph, is that when you start to begin to see the spike, a bit hard to see here, but we're talking about the beginning of the Industrial Revolution. So we're starting to see machines that are using carbon-based fuels. And so by the time you get to 1950, you're starting to go somewhere we've never been before.
Absolutely, yes. So that low there, right before the spike, that's around the time when the Industrial Revolution began. And you can see this just very quick increase in CO2 concentrations. And that's right, in 1950, we surpassed the 300 part per million.
So our planet, in spite of this, is trying to cope with what we are doing. And can you talk about how the planet's responding to this?
Sure. So first of all, our planet is very wise. It tries to keep itself in balance. And the oceans, vegetation, and soils have mechanisms to absorb carbon dioxide from the atmosphere. However, what's happening is we are releasing carbon dioxide too quickly, and we're not allowing these mechanisms to take up that excess carbon dioxide. So if you look at the percentage of carbon dioxide that's released per year into the atmosphere, 26% of that CO2 is absorbed by oceans, 28% by the land surface, and the rest accumulates in the atmosphere. So this next video animation, it's really cool. I love it because it shows our Earth breathing. And what you see over land, the green, means vegetation growth. And these are measurements from a sensor called MODIS on board NASA's Aqua satellite. And then what you're seeing in the atmosphere, those are CO2 concentrations measured with AIRS, also on board Aqua. So it starts from January 1st, and around May, there's a peak in atmospheric CO2 concentrations. And then around September, October, there's a minimum in atmospheric CO2 concentrations. And what's driving this cycle is primarily the vegetation in the northern high latitudes. So you can see that during winter, there's no green in the northern high latitudes. The land surface freezes, and there is no exchange between the vegetation and the atmosphere. In the spring, when the thaw rolls around, vegetation turns on. It's like a binary switch, and it starts growing, and it starts taking up huge amounts of CO2, enough so that we can see that the concentrations change dramatically.
So vegetation, one of the areas that there's vegetation is actually in the polar region that is frozen, that we now call permafrost, but it's not so permanent anymore, and that's a concern too, isn't it?
Yes, absolutely. So permafrost are soils that have been permanently frozen for at least 2 years, anywhere from 2 years to decades to hundreds or even thousands of years. And as you can see in the figure here, these areas of permafrost are primarily in the northern high latitudes, especially in Alaska, Canada, and Russia. And so permafrost is like a freezer. If you put food in your freezer, it'll be preserved. But if your freezer breaks, it'll start to heat up. And as it heats up, bacteria starts eating your food, and the food starts to rot. And the methane and carbon dioxide and other gases and chemicals and nasty stuff will be produced. But permafrost is like that. So permafrost has vegetation that's trapped in the soil, vegetation that has just died, that could not decompose, and it freezes. And as temperatures increase above 0 degrees, the permafrost starts to thaw, and that vegetation then starts to decompose, and the carbon that's part of that vegetation is released into the atmosphere as carbon dioxide or methane. And actually, estimates of how much carbon is stored in the permafrost is that it's it's more than twice the amount of carbon that's in the atmosphere. So it's a huge amount, and it's very concerning. I do a lot of field work in Alaska, and I see the evidence of melting permafrost. You see it, there are these slanted trees, because the infrastructure, the ground just, as it melts, right, it shifts the ground. And so you have these slanted trees that are called drunken trees, and in some places it's so prevalent that you have large patches of forests where you see these slanted trees. They're called drunken forests. So yes, it's very concerning.
So if you think about it, step back in the last 2 decades, it's the Industrial Revolution is happening with all the CO2, and now the question of what's coming with the release, potentially, of the permafrost will be upsetting the cycle yet again, the carbon cycle wanted.
Absolutely, yeah. So it's a cycle that intensifies.
So Carmen, while we're in the polar region, let's talk about also the ice sheets and glaciers and what's happening there. Give us the latest on that.
Yeah, so as we see that it's warming, I mean, not only is permafrost decreasing, it's melting, but actually when we look at the ice sheets, and we do have quite a lot of missions and airborne and satellite missions that look at the ice sheets and see how they're changing. And so one of the missions that we have is a mission that I'm working on a lot. It's called the GRACE mission. It's a gravity recovery and climate experiment, and we're going to talk about that a little bit more later. But what we see here in this graph is what is happening to Greenland since 2002. And what you see in these colors is the white color is where nothing much is happening. And then you see in some of these areas, it's actually turning red. And this is the areas where the Greenland ice sheet is losing mass, water mass. It's melting and it's going into the ocean. And when you look at the graph, that just shows you how much it is doing that over time since 2002. And we've talked about seasons. So seasons do a lot. They also happen in Greenland. So that's why you see this up and down in this curve. So in the winter, there's snow. So snow increases the ice mass of Greenland. But then in the summer, it's melting. And what you see also here, so it's steadily declining. So it's melting more than snow gets onto the ice sheet.
Yeah, I think I read somewhere that the warming is almost twice as much in the polar regions as other places.
Yes,
is that right?
in the northern polar regions, because it's amplified in that region. So, but if we go to Antarctica in the south, it's slightly different, and it's a slightly different environment. In Greenland, the atmosphere is usually warmer. In Antarctica, it's actually a lot colder, and I can say that. I've been there actually on a research cruise, and I've been out there, and I was trying to take pictures of the environment and of the icebergs. And as I was doing that, I took off my glove, and I was trying to push down the button. After 5 minutes, I had to stop with the pictures. It was too cold. But then what you see is also happening in Antarctica. There are some regions that also turn this reddish color, dark red, and this is actually why, this is actually because the ocean is affecting the ice sheet at that point.
It's warming too.
It's warming too, and it's melting the ice from underneath, so more ice is flowing from the land into the ocean.
And let's talk about the sea rise and what's happening with the oceans too.
Yes, so in the next picture, we just see again like what it really looks like. You know, we looked at the data, but now here you see some actual imagery of glaciers and how they're decreasing over time. And so that, of course, then contributes to sea level rise, sea level change. And so in this animation that Jason is showing us with the ice on Earth is showing data from another satellite mission. This satellite mission, the first one, was launched in 1992 and was called Topex Poseidon. After that, they called it the Jason missions, and that's what they're still called. We just recently launched the third Jason, and what these satellites are doing, they are called altimeters. So they have a radar beam that they send down to the surface, and it bounces off the surface of the ocean. The satellite receives that signal back, and by flying over it and doing that time after time, you can actually see how sea level is changing over time.
And it's very fine. I've heard it's like the diameter
yes.
of a quarter or something, or less, or the
yes,
edge
it's
of
less
a
than
quarter.
that. Yeah.
Yes.
So it's that precise.
And so you have the melting of the glaciers and the ice sheets contributing, and the water, because it's warming up anyway, it's rising.
Yes.
So
yeah, that's it.
And so there's a concern about what that will mean to coastal areas everywhere.
Yeah, exactly. And what we see currently, we have about 3.3 millimeters per year, but over the time that we have this mission, the Topex missions, it already accumulated to a couple of inches. And so if you would say that continues over 100 years, just at that steady rate, we already have a foot of sea level rise. And then when you add all the other effects that we have in the ocean and along the coast, with the tides come on top of that and the storm surge, so that just adds up. And as you can also see here in this animation, sea level is not flat everywhere. So coasts are impacted differently just because the ocean is moving and distributing the heat in different ways. So in this animation, the blue colors show where sea level is lower than usual, and the red to white colors is where sea level is higher than usual. And what we have here in the Pacific, where you see like a lot of this red and white developing, that is what is called the El Niño Southern Oscillation, and that's something that's very much of interest to us here in California because it impacts our weather so much.
Now, I know you work on GRACE, and it's also one of my favorite satellites because it's so ingenious and so counterintuitive about how you've come up with these measurements. And
yes.
Very clever what you scientists do. And I wonder if you could describe, let's just talk for a little bit about the technology of a NASA satellite, this one particularly.
Yes, yeah, and I fell in love with GRACE when I wrote my thesis. That was my first project, and I've worked on the project ever since. And I liked it because it was so unique, because it's actually a mission that doesn't look down and scan the Earth. It actually has two satellites that follow each other in orbit and measure like each other. So I actually brought two GRACE satellites here, which are just phones, but they're very, very similar to the GRACE satellites in terms of like what type of technology is in here. So the phones, when you flip them, right, then your screen flips too. And so there is a little instrument in here that's called an accelerometer. And the GRACE satellites actually have one on each spacecraft too, just to see how the satellites are moving. And your phone also has GPS, right? You can navigate with it. That's what the satellites do too. They're getting located in space. We want to know where they are. And why do we want to track them so precisely? Because we want to measure the gravity, the gravitational pull on the satellites. So what these phones do not have is the link between them. So the GRACE satellites have a microwave link between them where they can see how the distance between them changes over time. And so why would they change the distance at all? So if we imagine some kind of like heavy thing on Earth and the satellites are approaching, and the first satellites comes near that mass, it's actually getting pulled by that heavy thing on Earth, and the distance between the satellites increases. So now they fly over, and the second satellite gets pulled too, so now the distance decreases again. The first one leaves then and gets further away from the mass, so the distance increases again. So they bounce back and forth with the gravity field.
And this can show us not only about the oceans, I don't know if Jason, you can show it, but the Amazon is an area that amazes me. You fly over it and you see the seasons, the difference there between the monsoon seasons and not.
Yeah.
The amount of water, you can measure the amount of water.
Exactly. So when you first think about gravity, you think like, oh, it's not changing very much, but it's actually changing quite a bit. Because there's a lot of water moving, and as you said, here over the Amazon, blue again is more water and red is less water. You see the dry and rainy season, how it's changing over time.
And let's bring this back to California and,
so
and talk
now
about what
we can
see with
basically weigh how the water is changing everywhere. And so we can do that also for us in California. And what we see here is how our water table then is developing over time. So now GRACE can actually not only look at the surface, but it can actually tell us something about the groundwater. And here in this graph that's moving, this line that's moving, we see in 2011 how the drought starts and what the GRACE satellites see. Like you pull a lot of water from the ground. And then from the aquifers. And then in the end, we just saw this blip that was the rain we had last year, where some of that groundwater is recovering.
But that recovering from just one big rain is not going to do it with the aquifers,
Exactly.
is it?
So we still need to be careful with our water resources, yes.
And also, as a result of this, we're seeing other impacts in the breadbasket of the valley, the California Valley.
That's right. So one of the effects of overdrawing from aquifers is that the ground can sink. It's called subsidence. And that's something that we can measure with satellites from space. And this is an example of that. This is in the Central Valley. And we can measure the subsidence in the order of inches. So what you're seeing here, the blue areas are areas where there's been no change, but the cyan and the pink areas are areas where there's been some subsidence on the order of 12 to 24 inches. That's up to 61 centimeters, which is a lot. And this is over a very short time period. It's within 2 years, but it's right during the drought when there was a lot of groundwater being withdrawn.
And I think there's some images too that you
That's right. So here's some examples. This is the one on the left is not recent, but that really shows you how much subsidence has taken place in the Central Valley of California. That's actually a pretty famous picture. The person standing on the bottom has the year, which is 1977, and at the top you see it says 1925, and there was 9 meters of subsidence in that period of time. That's about 30 feet. And then the image on the right is a bit more recent. That's an oil well, also in the Central Valley of California. And 3 years prior, the oil well had been painted with orange paint. And so within that 3-year time frame, the ground subsided 1.5 feet.
Another example of how much change is happening right in front of our eyes.
Absolutely, yes.
Yeah. You know, I'm also interested in the question of, with all this going on, in how you decided to get into these fields. What made you decide that you wanted to be in this field of work? I'm really curious.
Yeah.
Yeah.
So, well, I started out actually studying mathematics, so theoretical mathematics, and I did my master's in math. And then I thought, okay, so what am I gonna do with that? Everything was so abstract and nothing really applied, and I really wanted to do something that relates to the world and has an impact on people. So for my PhD, then I decided to switch to physics and study the Earth. And this is how I started off with working on the GRACE mission and wrote my thesis about that, and then came because it's a JPL mission. After that, I came here. I moved from Germany to the U.S. to work here, yes.
Straight from, so from a student working on GRACE, and now you're here as a scientist.
Yes.
That's great. How about you, Erika?
So for me, I was born and raised in Panama, and it's a beautiful country with an exuberant nature. And I was fortunate that my parents were very outdoors. So from a very young age, I was often outside, surrounded by nature. And this developed a curiosity and a love for nature. And I also had a great interest in technology. And I remember as a child thinking, it'd be great when I grow up if I can use technology to study the environment. So years later, when I was in university, early in my bachelor's degree, I discovered this field called remote sensing, which includes the observation of Earth from space. And so my master's and my PhD then were focused along those lines. And then one thing led to another in my life, and now I observe Earth from space here at JPL, and I'm loving it.
That's great. And when you look ahead, I mean, there are a lot of challenges facing this. And what do you say to people that, you know, some of this information is sobering, this is challenging, and how do you talk to people about the future? And how do we? Sometimes scientists talk about mitigation and adaptation. What do you say? How do you look forward to it?
Yeah, so that's a great point, and I think it's important for people to understand what's going on with our planet and the information that we get here through satellites, and what we're understanding about our Earth is very important. So I think the most important thing is we can make a change, and we can all make little changes that are beneficial for our environment. Whatever your stance is, I think we should all take care of our environment, because a healthy environment is a healthy human being.
I know you like this image of the Earth is in our hands, isn't it? Yeah.
Yes. I mean, it's beautiful because it shows the fragility of our planet, and we don't have infinite resources. We really do have to take care of it.
And Carmen, how about you? How do you talk to people? What do you say to folks?
Yes, I mean, so being at NASA, having the opportunity to look at all these observations, it's just a great thing, and I think we contribute a lot to society just by doing these measurements and providing these information. And I hope people were able to see that, I mean, we're able to study these remote areas that have so much impact on our lives. So yeah, we have a great opportunity here, and that's what I love about working here, that we do make some impact.
Well, I take great comfort in knowing that you two are doing, and all your colleagues are doing what you do. And I just want to thank you so much for what you do and for being here tonight. Thank you.
Thank you very much.
You know, we began this evening talking about Explorer 1, a satellite 60 years ago that gave us the very first space science discovery and helped to answer the question of why we live in such a special place, in such special circumstances, you know, protected by the Van Allen radiation belts, that we can enjoy life here. And we've progressed to talking about all this technology that we now have in this fleet of science instruments that NASA has to understand a very, very changing world that we live in. And as we mentioned a moment ago, there's, for scientists and others involved in this, there's mitigation, which means changing your behavior to try to address what is happening to our world. And there's adaptation, the fact that we will face the environment, a different environment, and find ways of adapting to it. And through all that, we have NASA to inform us as to what information we need to know in order to do those things. And I think that is so comforting to me, because even though we have NASA as a space agency, it's still, this is the only planet we know we can live on. Thank you so much for coming. We enjoyed it very much. Thank you. And thank you, Jason. Thank you, Dr. Conway. And one final thought. Run, don't walk to, when you get home, not only to these great software applications Jason has told us about, but go to our NASA climate site. It's www.climate.nasa.gov, and there you will find the vital signs of our Earth that you can check like your blood pressure every single day to know what's going on our planet. Again, thank you very much. For those who are here on Ustream, hold on, we'll be back in just a moment to answer your questions. Thank you. Okay. Again, for those who weren't here earlier, your questions we'll be happy to answer now. If you have a question, please come up to the mic, which is right here in the center. Nailed it.
Yes, get a little high. Okay.
It's just me. I must be out of the frame or something. What happens?
Okay, why don't we start?
Okay. I have a little story related to this picture, if you allow me. I was a little boy in city of Cairo, Egypt, when the Russians and the American sent those satellites. And in Boy Scouts, they were telling us about the orbits and the artificial satellites and so on. And I went to the American embassy in Cairo and saw this picture, and I told them what it is. And they said, oh, this is a Jet Propulsion Laboratory. Where? In Pasadena, California. Okay, then I asked my teacher in junior high school, and he said, well, I told him I want to work at the Jet Propulsion Laboratory. He said, you have to have a PhD in order to get there. I went back and asked, what is a PhD? And then where is Pasadena, California? I took the map, went to my parents. I said, I'm going to work at the Jet Propulsion Laboratory, and I'm going to have a PhD. About a decade and a half later, I came to the Jet Propulsion Laboratory after having studied jet propulsion in Cairo and in Germany and in the United States. The day I started here, the moment I looked at this picture, starting at JPL, I could not believe my eyes that I'm really here. The moment I met also Dr. Pickering, it's like meeting God. And I told him the story. And I said, well, thank you for inspiring a little boy from Cairo, where I was looking at sky to see those artificial satellites. And I was inspired. Okay, I got my PhD in jet propulsion, and I was introduced to Dr. von Braun by my professors in Germany, Professor Herbert Knote and Professor Herbert Schmidtlein. And then I worked here in the United States with a student of von Carmen himself. I mean, and here I am, 60 years later, after, looking at the sky. By the way, I never saw this artificial satellite when I was a little boy. And 60 years later, I'm, celebrating.
Well, thank you for sharing that. It's a great story.
Good story.
All right. Thank you, sir. All right.
Everybody?
Yeah.
And
thank you. Next question, sir.
Well, that's a hard act to follow, but very specific comment question. In the discussion of global warming and climate change and the CO2, I think there's a very important measurement that is rarely discussed that I think is a mistake, and that is the isotopic signature of the CO2.
Yeah.
And the fact that the fossil fuel has been buried so long it has no carbon-14. It's all decayed. And so you can, by measuring the percentage of the CO2 in the atmosphere that does have carbon-14, which is created only in surface carbon,
top of the
you can prove that it's not coming from the ocean, that the rise in CO2 is not temporary, that it's coming from fossil fuel mostly, and for other human activities. So
that's known as the
I'll just make that comment.
Yeah. The Seuss effect, it's not work done at JPL, that's all.
Well, it's rarely mentioned.
It's rarely mentioned. It's also really hard to do. And so I teach an introduction to climate policy class almost nobody knows about. And I do teach it to my students, but it's very difficult to get them to understand the measurement. And that might be why, too, it's so rarely mentioned. But thank you.
Okay. For that. Very good point. We also have questions coming in from our Ustreamers and our YouTubers. And one here is, Space TV asks, is there any technical program out there is designed to remove carbon from the atmosphere?
Do you want me to say? Okay, so lots of ideas. One, for example, is that we could remove carbon dioxide from the atmosphere by dumping more iron into the oceans and sequestering it that way. Problem then is you create low oxygen zones in the ocean, which is bad for sea creatures. There are technological ideas about pulling CO2 out of the air and then turning it into something else. Maybe burying it in the ground, but maybe turning it into some sort of a product. The one that probably gets the most attention, when there's any attention, is the idea of growing crops, burning them in power plants, and then sequestering the CO2 from the power plant. That one's called bioenergy, carbon capture and storage. So there are ideas, but no one actually is doing it yet on any kind of scale. And the economics are really difficult to see working out.
In question here.
Dr. Gene Nelson. First, a little comment about that previous question. Dr. James Hansen, former NASA scientist, recognized a very simple low-tech solution, which is called reforestation. Anyway, I'm going to go on to my question. And that is, this is more related to the history of space exploration. I wanted to find out what your take is as to the reason why President Eisenhower said, when he found out that the Army could, in fact, put a Explorer 1 in orbit in late 1956, why did Eisenhower say no? Do you know the real reason? Because I'll give you a hint. It's another space program that has its strong roots in California. So let's see what your take is on this. Another space program based in California. In fact, I'll give you another hint. All the launches were from Vandenberg Air Force Base, right close by here.
Well, I assume you mean the Air Force program, but there's a committee that was put together starring Jack James from JPL and some others, as well as a lot of independent scientists, to choose which of the competing proposals should be the IGY launch vehicle. And that committee chose Vanguard, not the Eisenhower White House. So if that's the incident you're referring to, that committee made the choice and the White House blessed it. The scientists on the committee thought they were getting more payload out of Vanguard. And I think, and Jack James, in the memos he wrote, said they were really de-emphasizing the difficulty of making a launch vehicle that was reliable.
As was proved on December the 5th.
Well, as was proved, by the Vanguard attempt, in which the JPL and von Braun folks knew because, half the launches failed. It was that bad in the early space age, and the earlier you get it, the worse it was. Really making rockets reliable was a huge achievement, and we, the United States, forget about the German investment during World War II. We, the United States, spent in the 1950s alone about a quarter of $2 trillion current dollars developing rockets. It was an enormous investment for that period of time.
I agree, but the Corona program really is a fascinating story, and unfortunately, it was classified until 1993, and that story needs to be told. So that was my little plug for Corona.
Oh, you were talking about Corona. The Dwayne Day has been the historian of that.
Oh yes. Yeah. I've talked to Dwayne when I was in D.C. So.
Yeah.
Yes. Some of the Corona's there in the Air and Space Museum now. In Washington. Thank you, sir. We have a question Milan asked. I don't know if it's Milan, Italy or not. Maybe so. What new explorations are planned for the near and far future? Maybe we could start with Grace.
Yeah, exactly. So I'm very excited because after we had 15 years of Grace from 2002 to now, we just ended the mission because of its long lifetime, and so we're decommissioning those satellites. But we want to continue the measurement because we talked about climate and how it's evolving over time, over these long time scales. So NASA has decided to again work with the Germans on a new couple of satellites called the Grace Follow-on mission. And those 2 satellites are actually ready to go up in space right now. They're at the Vandenberg Air Force Field to be launched later this year.
All right. Any others?
Yeah, so I can speak to some of the terrestrial-focused satellites that will be, or instruments that will be launched shortly. First of all, there are going to be 2 instruments on the space station launched this year. One is called EcoStress, and that measures evapotranspiration. And the other one is called OCO3, and that measures CO2 concentrations in the atmosphere. And it's also looking at something called solar-induced fluorescence, which is an indicator of photosynthetic activity of vegetation. Then in a couple of years, in 3 or 4 years down the road, there's a satellite, radar satellite called NISAR, and that's together with the Indian Space Agency. And then around the same time frame, there's another one called HISPERI, and that's a hyperspectral sensor. And by the way, 2 things that are really important here. That international collaboration is really something fundamental in the work that we do. As you heard Carmen talk about GRACE, that's a joint collaboration between JPL and Germany. NISAR is with the Indian Space Agency, and we've had many other missions together with other space agencies. And the second thing is that NASA has a free data policy. So all of the data that's collected by NASA satellites or instruments is free. You can download it, as well as data collected by NASA instruments, airborne instruments. Sorry.
Sir.
Yeah, well, first, Jason, is the EYES program available for Linux, or is it only available for insecure platforms?
Yes, I've gotten that question before. We are developing Linux right now, but we don't have it currently. But we're also going to move to the web, in which case it'll be fine for Linux.
I remember in 1968 or so when Bill Sjogren and his colleague Muller, whose first name I've forgotten, discovered mass concentrations on the moon using orbital variations from Lunar Orbiter. And I think between that discovery and the time of GRACE, which originally Bill Sjogren proposed shortly after Lunar Orbiter, I think GRACE and COBE kind of competed neck and neck for the most canceled mission. I think COBE was approved and canceled more than 70 times. I don't know if GRACE has broken that record or not.
But yeah, I mean, that always happens, right? That these concepts exist for a long, long time, and all of a sudden, yeah, you get the funding and you can fly
and then
it.
you finally realize it's important.
Yeah.
Yes. The third is it's not so much a question. Well, maybe it is a question. I've been astonished for the last 30 years or so that people who have noticed that human activity, and especially the use of carbon in the energy sector, is affecting the climate, are quite worked up about it and simultaneously oppose nuclear power, which is the only thing that can work if you look at an entire system and not just, a solar panel here, a windmill there, a dam somewhere, the waves off Norway. If you look at the entire system as a system, quantitatively, you reach the conclusion that nothing but nuclear can work. And by the way, nuclear power is the safest ever way to make electricity by an extremely wide margin. 43 deaths in 60 years compared with 30,000 deaths a year from coal burning in the U.S. alone. That's not an externality. There are no externalities from nuclear power because everything is put away somewhere. There's just no externalities. So that's kind of an astonishment to me that people who claim to be worked up about carbon emissions from the energy sector simultaneously oppose the only solution that'll work.
Okay, thanks, sir. And now another question we have is, how long have they been tracking climate change by satellites? When did climate change by satellites go?
So it started with the Landsat program back in the early 70s.
Well, it depends on which aspect, right? The weather satellite data it also extends back into the 70s, and some of the early passive microwave radiometers too. But none of those missions were flown for climate right? They all had a different purpose. So there's climate data satellite-based climate data going back that far, but the first satellites really dedicated for it are the Earth observing systems satellites, which are post-2000, or sorry, 99 for Terra.
Sir.
Hi. It's it's been suggested in the last year by the current administration that to further explore and put more money into exploration outside of the low Earth orbit area. I don't remember the specifics of it, but I remember hearing the proposal that there should be massive cuts to the Earth science program at NASA, and as far as I remember from what I've read, that those haven't come to fruition yet, but they're still possible. And what I was hoping you guys might be able to talk to a little bit is, I would assume that you guys have a contingency plan in case all of a sudden those cuts to Earth science come through. And kind of what I would like to know, and I think it would be really good to know for all of us, is should those cuts happen, what would we lose? Like, what current missions would we have to shut down? What missions in the pipeline would we not be able to see launched? And just kind of speak to that. What would we lose in slashing the Earth science budget?
I don't want to dodge that question, but I want to answer it honestly. Is that my experience is that no matter where you go in the country, people are interested in and I'm talking about elected officials, are interested in what's happening in their part of the world and what our satellites and science instruments can tell them about what's happening in that part of the world. It could be a drought in Texas. It can be concern about sea rise in Florida or Louisiana. I think that the country as a whole we're in pretty good stead now with NASA. So I wouldn't lose any sleep over that. I think our elected officials understand that we're providing, our job at NASA is to provide the information so that policymakers can make good decisions. And from what I see, I think we're doing fairly well right now. So, thank you very much. Yes.
Hello. I got really excited about the earlier isotopic ratios of CO2, which I would appreciate if I could follow up on that with you and the gentleman who brought it up. But my question is, 60 years ago, there was no satellite in space. Space was empty. It was only like a space material. And now after 60 years, we have a space junk crisis. So I want to have like your and Erik's opinion about is there any lessons learned? What did we do in the last 60 years, and could we have done it differently? It's huge. When I was born, space was touched by humans. But when my parents were born, space was not touched by humans. I want to hear your opinion about it and see what's the lessons learned and what could we have done it differently. And if we go back to 60 years ago, as a historian or as a scientist, do we do everything exactly the same that we did?
Okay,
Thank you.
sure. So nowadays there's an international agreement to design satellites so that they can be deorbited. And so what could have been done differently is simply to have done that earlier, right? And done it at the beginning of the space age instead of when we actually did it, which is maybe 20 years ago. Maybe it's not even that long. But I mean, that's the fundamental solution. We didn't learn the lessons soon enough. Yeah.
As you said, now we have to have a plan. And with the GRACE mission, we had to add that plan, and we just decommissioned the satellites, which basically meant they deorbit, they burn up in the atmosphere, and that's how you get rid of them.
All right, we'll take one final question.
Thank you. Like the lady's parents just before me, when I was born 75 years ago, we had barely touched the stratosphere. I want to know from our guests what we can expect 75 years from now? I know it's hard to look ahead, but the pace of change is increasing and increasing. What's the most far out thing you can say 75 years from now? Any of you?
Wow. Okay. So the first thing that comes to mind, and I hope it's not 75 years from now, I hope it's 20 years from now, is we shouldn't be flushing drinking water down our toilet.
I think I was thinking a little further out in space.
Well, if further out in space is what we're after, heck, I figure, and unfortunately I know I won't live to see it, but I figure by then we'll have definitive evidence of whether there are other living planets in the neighborhood of the Earth. And I don't mean in our solar system. We already know that there aren't. Well, okay, I'll get into trouble again for saying that, but I'm already pretty sure there aren't other living planets in our solar system. But out there, that's what I think. I think that's the big thing I would expect in astronomy in the next 75 years.
And Blaine, if you will, one final question. What happened to Explorer 1? Is it still up there?
No.
No, deorbited.
It burned up, I believe it was March 31st, 1970. Our website should say it for sure. But it was a highly elliptical orbit, and so it burned up.
And Sputnik?
I think so too, but I don't remember exactly. I think that's burned up as well. Yeah.
So following up on my comment, I think thinking 75 years into the future and what we're learning about our planet, I think our lives will be much more in tune with our planet. You know, as we're learning, we'll see a lot of changes probably in the next 75 years. And hopefully we'll be more efficient, more conscientious about the resources that we use, more efficient in the resources that we use overall.
Okay. That's a good way to end. You've been a great audience. Thank you very much. Thanks for coming to JPL.